So applications of calculus to the physical world. Basically motion is what we're going to be looking at. And the key things for motion, so displacement we've talked about. Very often we just use the pronumeral x because we think about moving along the x-axis, but it doesn't have to be x, of course. And that is distance, but with some direction. Velocity, which is the rate of change. So the symbols we could use, obviously v for velocity, but because it is the rate of change, we could write it as dx dt. But very often when we're doing motion questions, we use this dot notation. It's actually Newton's notation for calculus. And so one dot over the top means the first derivative. But usually we just reserve it for these motion questions. So it's the rate of change of displacement with respect to time. Similarly, it's speed, but again with direction. So the plus or minus has some meaning. Acceleration then, well, acceleration is the rate of change of velocity with respect to time. So A, obviously, for acceleration, but it also then means it's the rate of change of velocity, so we could write it as dv to t, which therefore means it's the second derivative of displacement, so we could write it as d2x to t2, and using the Newton notation, it's the second derivative of displacement, so x with two dots on top. And of course it also means you could write it as v with one dot on top because it's the first derivative of velocity. And acceleration is the interesting one because with displacement you have displacement which is distance with direction, and velocity is speed with direction. Well, acceleration is acceleration with direction. We sort of use acceleration for both contexts. It's a weird one. Now, you might have heard people talk about deceleration. Now, let me at this point say something. There is no such thing as deceleration. Okay? So there is no such thing as deceleration. So what we think of as slowing down, as far as we're concerned with this motion, is when acceleration is in the opposite direction to the velocity. And that's when you slow down. So it's still acceleration, it's acceleration in the opposite direction. So if you ever hear the term deceleration, that's what they're talking about. It is acceleration, but in the opposite direction to which you're travelling. So let's go back to this idea of travel graphs. But because we're now talking about displacement rather than distance, we now could have negative numbers as well. So on my x-axis, which in this case is the vertical axis, we have negatives now, which we don't normally see in travel graphs, but now we do. We know we can work out the instantaneous rate of change, or in this case that would be velocity, by working out the slope of the tangent at any point. Now, if I was to then draw the derivative graph, so x dot, underneath, there it is. Now, how could I get it from my displacement graph? Well, I know key things about the first derivative. I know that stationary points occur when the first derivative is equal to 0. So that's why I draw them underneath each other like this, because I can say, well, look, here at 1 there was a stationary point, therefore on my derivative graph, or my velocity graph, it must be the intercept here. And there's my other stationary point. What else do I know? Oh, well, I know that when the curve's increasing, the derivative is positive, so I have a positive velocity here between 0 and 1. And when it's decreasing between 1 and 3, it must be negative, and things like that. I guess the other thing I can look at is, well, whilst I don't know the equation of this one, it does have that shape of a cubic, and if you differentiate a cubic, you get a quadratic. I'm expecting to see some sort of quadratic shape there. The slope of the tangent then for this one, the rate of change of velocity is acceleration, so that would tell me the instantaneous acceleration at any particular point. And then I could draw an acceleration time graph as well using the same sort of ideas. If I look at my velocity graph, I see I have a stationary point at 2, therefore that must be when acceleration is equal to 0. But the other thing I know is that at t equals 2, assuming that's symmetric of course, at t equals 2 I've got an inflection point, and that also tells me that the acceleration would be 0 at that particular point. So it's confirming that velocity one. Differentiate a quadratic, you would get a linear function, so actually it ends up being a straight line, that particular graph. So those sorts of questions again. Distance travelled. Okay, well, I can look at my displacement time graph And I can see, well, that's 7 meters all up. Because remember, we've gone up to 2, but then down to -2, so that's another 4 I've travelled, and I've stopped at -1. So all up 7 meters I've travelled. Whereas the total displacement, how far away am I from my starting point? Well, I'm 1 meter away, but I'm in the negative direction, so it would be -1. Average speed is distance over time. The total distance we travelled was 7 over the time 4, whereas average velocity is displacement over time, so it'd be -1/4. Well, as we saw yesterday, we don't actually need the graph. I mean, the graph could be handy if we recognise it, but we don't actually need it because we can use our calculus if we know the equation of the graph. So in this one, they've given us the equation of the travel graph. X is equal to t cubed minus 21t squared. What would the acceleration of the particle be at time t? In other words, what would be the equation of the acceleration time graph? Oh, acceleration is the second derivative, so we differentiate it twice. So velocity would be 3t squared minus 42t, and acceleration we get 6t minus 42. Find when the particle is stationary. Well, when is it stationary? Stationary when it's not moving, velocity must be equal to 0, but also it ties in nicely with the language we use in calculus because it's the first derivative equals 0, which is stationary points. So we know it's stationary when velocity is equal to 0. Now when you're solving this problem, don't just say v equals 0, explain why it's equal to 0. Like, why can I make it equal to 0? Well, I know I can make it equal to 0 because I know that the particle is stationary at that time. So 3t squared minus 42t, solving that, I get 2 possibilities. So it happens twice. So initially it's stationary, and then again after 14 seconds it'll be stationary as well. So this one, they've given us the equation for the acceleration time graph. So there it is, 2 plus 6t, and they've given us some initial conditions. It starts at rest, so velocity is 0, and at the point x equals 7, so it's not starting at the origin. This one is starting over at x equals 7. Wants to know where is it after 3 seconds. Now I'm going back the other way, so I've got to integrate. Acceleration's 2 plus 6t, velocity 2t plus 3t squared plus a constant. It's where constants can be really important unless you get lucky and the constant happens to be 0, because if you forget it, obviously it's going to change the equation. Well, let's see what happens. When t equals 0, v equals 0, so oh yeah, in this case we would have got lucky, constant is equal to 0, so if I had forgotten it, I would have still got the right equation. Will the same be for displacement? So integrate again. No, I wouldn't have been so lucky with this one, because when I sub in, the constant is equal to 7, and so there's my displacement equation. We want to know when t equals 3. So subbing in, we get 43, so we now know where it is after 3 seconds. It's 43, well, however you want to write it. It's at x equals 43, or it's 43 to the right of the origin, or some sort of explanation there. Now, of course, that problem with constants, we saw we could resolve that problem by not using indefinite integrals, but using definite integrals instead. So I could have said, well, acceleration I know is dv to t. So dv to t is 2 plus 6t. That therefore means that the integral of dv is equal to the integral of 2 plus 6t to t, and I make it a definite integral. Our conditions we were told, when t equals 0, v equals 0. I'm trying to find a relationship between time and velocity. I just do it as definite integrals. Now on the left hand side, when I ever have something like this, dv, 0 to v, I can just jump straight to that and say that's v, that's fine. The right hand side though, of course, we have to do some work. Sub in t, sub in 0, and we get the same equation as before. But now to solve this problem, dx to t is 2t plus 3t squared. So again, I'll make it a definite integral, but here's the lovely thing about this. I can get the answer straight away, because yes, the initial conditions were t equals 0, x equals 7. But now I can solve the problem, because I'm saying, well, I want to know what x is when t is 3. So the whole calculation will bring the answer out straight away. This time you'll notice I did make it x, rather than just going straight to the pronumeral, because it's not 0 I'm substituting in, it's 7. I suppose I could have just written x minus 7 down straight away, but it makes it obvious where that comes from. So subbing in, we get x minus 7 is 3 squared plus 3 cubed. Taking the 7 over to the other side, we get x is 43. There's the same answer. Okay, let's look at some, well, old ones, but some HSC questions. 2001 paper. Particles moves in a straight line. That's what we often look at here. So x is equal to this interesting equation, t minus 2 on t plus 2, which I guess is like some sort of hyperbola, when t is measured in seconds. Okay. So what's the initial displacement was the first thing they want us to find. So that's just a simple substitution question. Sub that in, I get -1. So whether you say, oh, it's at x equals -1 or it's 1 metre to the left of the origin, there's my answer. Show that. Okay, so it's basically an algebraic fraction question. Oh, but then we've got to do a bit more. Hence, then go and find the expressions for velocity and acceleration. Okay. Well, I think it's going to be easier to start with the 1 minus 4 on t plus 2 and show that that's the same as t minus 2 on t plus 2. I think that's an easier way to go because it just becomes an algebraic fraction question. And t plus 2 minus 4, yeah, that gives me what they wanted. So I've shown that that is the same expression. We now have to find velocity and acceleration. We've got to differentiate these things. So velocity, well, differentiate 1, we get 0. Here I'll just use my reciprocal rule, minus the derivative on the function squared. I get 4 on t plus 2 squared. Now I have to differentiate that one. Again, I can use my reciprocal rule, that minus the derivative on the function squared, we get minus 2 t plus 2, but of course multiplied by the 4 that's on the top, and there's my acceleration. Is the particle ever at rest? So this now brings in the other sorts of questions. They ask us to interpret these things. What's happening with the motion? What's the particle doing? Is it ever at rest? And I give reasons for the answer. Okay. They're not simply going to go yes or no, 50-50 chance here. They want to see some sort of explanation. Okay, there's our velocity. It's saying, is that ever at rest? Like I said, well, no, I know that can never equal 0. I've got a fraction with a constant on the top of the fraction. It can never equal 0. So therefore, no, it's never at rest. Possibly I could have written that better by actually writing that explanation there that, well, we can't have a constant on the top of the fraction, that sort of thing. But there it is. I've given a reason. I'm saying, well, look, that can't ever equal 0. So no, it's never going to be at rest. What is the limiting velocity as time increases? Because it's moving. We just say, hey, it's never going to stop. So what velocity is this thing going to approach? In other words, what's the limit as t approaches infinity of that expression? And that's what they're really asking me to find. Well, the limit as t approaches infinity of that would be 0. When we're dealing with our limits as we approach infinity, the key is you're looking for the coefficient of the highest power, which if I was to expand the bottom out would be t squared. It has a coefficient of 1. Well, on the top, there is no t squared term, so I'd have 0 on 1, which is 0. Of course, another way is I could actually think of the graph. Now that I have the equation for velocity, that is a hyperbolic shape, and I know that approaches the axis as time goes towards infinity. So I could just draw myself a little sketch and go, oh yeah, there you go. Whichever way I do it, there's my limiting velocity. So it doesn't ever stop. It's going to get very, very slow. It's approaching 0, but it never actually stops. 2002 question. Once again, we're moving in a straight line. It's a trig equation this time. X is sine 2t plus 3. Sketch the graph. Oh, this is drawing a trig function. We know the amplitude is 1. We've shifted it up 3 units, I can see that. The period is pi, so I'll mark off my divisions every pi on 4. So remember with trig graphs, basically I want to plot the boundary points. And there are 4 boundary points in a period of a sine curve. Alright, so I've marked off my t-axis on those divisions. Because I'm shifting it up 3, instead of going between 1 and minus 1, I know I'm going in between 1 and 4. I've just dotted in the axis there so I know where the sine curve's winding around. It just helps me with the plotting of the points. Now what do we know? We know that sine would normally start at the origin, but we've shifted it up 3. So there's my first point. I would then go up to the amplitude and then down, and we have our pattern. And there's my travel graph, my displacement time graph. Using your graph or otherwise, find when it is at rest. Now they've given us the hint here, using your graph. you don't want to be wasting time with this sort of question and going, oh, okay, well, let's differentiate it. Then I'm going to solve when is that equal to 0. When I've got a picture and I know something about the picture, I know the stationary points because I can see them. And so there they are. I can just simply now list them because I know it's going to be whenever the velocity is equal to 0. In other words, when the derivative is equal to 0. So the stationary points, that's what I'm looking for. That was at pi on 4, and then the displacement was 4, and the next one was 3 pi on 4, then 5 pi on 4, and then 7 pi on 4 was the final one there. And that can save ourselves a lot of time just by having knowledge of what the picture looks like rather than using the calculus. Describe it completely. Oh, I know you love these sorts of questions where you actually then have to, oh, hang on, words, this is maths. So I think I might have got a bit carried away, as I usually do. How did I describe it? Oh, here we go. I'll use some big words here. The particle oscillates between x equals 2 and x equals 4 with a period of pi seconds. So I've pretty much described the key pieces. I've talked about the amplitude of it. I've talked about the period and things like that. Okay, so 9b, we'll play with those ideas.